there's many different ways of looking at that. You can see that in a table. If an x value goes to two different y values, it's not a function. On a graph, you guys ever heard of the vertical line test?
Yes.
A vertical line test is basically you take a graph and then you take a vertical line. And if that vertical line touches only one point throughout the entire graph, it passes the vertical line test. Therefore, it's a function. Before I forget this, I think this might not be working because that's on mute. So that's how that works. Another way you would see it is sometimes on graphs, you might have a parabola. Okay? Does that parabola pass the vertical line test?
No.
Yes. So for every point, it only touches one spot. Now, now does it pass? That's not a function. Okay? That won't be a function because that vertical line touches it in two spots. It's a very simple concept to get across. We don't really spend a ton of time identifying functions right off the bat. Later on, we talk a little bit more about it, but just to give you an idea, that's really all 2.1 was about. As I said, we didn't really need to spend a lot of time on that. So just remember, when you're dealing with a function, for every value of x that you input, it only spits out one value of y on the output. Okay? X just can't be in two places at once. And then that gets us into quick graphs, 2, 3. You guys are going to go a few times today because you might not have been shown how to do some graphing real fast. In this book, there are a few sections that we get into that you just kind of want to get a rough idea of some what are called quick graphs. Because when you're dealing with quick graphs, you're going to be able to identify x-intercepts, y-intercepts, and some intersection points by using some simple usage of systems of equations. But it all starts out with being able to work with slope-intercept form or with standard form. We all talked about slope-intercept form yesterday. We all remember that was plain old boring y equals mx plus b. And I'm going out on a limb that if I gave you something to graph in slope-intercept form, that won't be an issue. It's something you guys have been, beaten over the head for quite some time in how to work with. Am I right? Oh. The other one is standard form. Now, standard form really, if you recall back from your Algebra 1 class, it looked like this. AX plus BY is C. Do you vaguely remember that? It's okay if you forgot it. It's not that big of a deal. Okay? And with that, there were some simple rules that came along with it. I think the first rule was A and B both can't be 0. Let me move this up a little bit here. If they both equaled 0, then you would have 0 plus 0 equals C. You won't have a graph. Okay? You could have x equal to 0. That means you have y equals a number. If you have y equal to 0, then you have x equal to a number. Bless you. That allows you to get both vertical or horizontal lines that way. That they just both can't be. The other part was the GCF. You remember that, right? You simplify A, B, and C. So for example, if it was 12x plus 6y equals 18, you can divide them all by 6. You can simplify them through. It's something like that. You guys have all seen that before. It's not that crazy. But what's nice about this, what's really nice about this standard form is that you can use standard form to graph like that. And the reason is because it allows you to find your x and your y-intercepts with one step. So let's think about what an x and a y-intercept looks like again. See if you remember. What is an x-intercept? and you don't have to have a fancy graph like I do. If I have an x-intercept at 6, what's my value for y? 0. Everybody agree? So your x-intercept, at your x-intercept, y equals 0. And then at your y-intercept, what's x equal? 0. So if I have a graph, that's written in standard form, if I set y equal to 0, I can get my x-intercept. Same thing, if I set x equals 0, I can get my y-intercept. Just by covering and solve. You ever seen that before? You're shaking your head, so that's not new. I thought it was new to you. Let me show you an example. I have 2x plus 3y is 12. And once again, don't worry about graphs. You don't have to be fancy, you don't have to be perfect. What I want to look at here is if I want to get the y-intercept, if I want to find the y-intercept, that means x is equal to 0. Cover it up. What's your y-intercept? 4. What's your x-intercept? 6. There's your line. Done. That's it. You don't have to put it in slope-intercept form to solve that. Graphing via your x and y intercepts when you're written in standard form is awesome. Okay? How many of you guys have seen that? A couple of you? Okay. The rest of you guys are probably going, I just had to do all that work and solve for y how many times?
That sucks.
It does suck, doesn't it? It's so much easier now, isn't it? Yeah, and that's fine. Because what's going to happen as we go into it, you're going to see, if you think about all those different times that you worked with systems of equations, it was always 2x minus 6y equals 11, 4x minus whatever y is 13. You could have covered and solved and done those quick graphs right away, got into your intersection real quick then, if it was a viable way of doing it, instead of solving for y and going through it. That's why we start to show you guys these things, because eventually it's going to turn into an inequality like that, and you're going to shade regions. We're not there yet, but it's going to turn into a problem like that. What we call those are linear programming or constraint problems. If you knew anybody that was in Algebra 2 last year, they hated it. Yeah. Who was it? Or are you just shaking your head knowing that they hated it? Yeah, I don't think there were many students that enjoyed linear programming. So, but this is why we teach you guys these quick graphs, because it makes everything else so much easier later on. All right. So let's look at some more. Same idea. If I'm going to do this via quick graphs, like I said, for right now, as I'm doing quick graphs, I'm not even going to look at a graph. I'm going to fudge it. I'm going to put it on a piece of paper. I'm going to label my x-intercept, label my y-intercept. I'm going to connect the dots and call it a day. Okay? So I have 3x minus 2y is 6. When I start this, I cover up the y. What's my x-intercept? 2. I cover it up. What's my y-intercept? -3. Good. I'm glad you caught the negative. Done. You're probably cursing your Algebra 1 teachers right about that. And there's absolutely nothing wrong with going back and putting this in the slope-intercept form, but
Why didn't they tell us this? Do they want us to look at things?
you know,
Drawing the graph.
I think it's so that we know how it works.
yeah, and there's nothing wrong with going through this. I mean, there's a process behind everything, but as you get to the upper level stuff, you're going to start to see that you kind of waste a little bit of time every once in a while here or there. But it's not. The main reason why they had you guys working stuff into standard form was working with literal equations. And that's just moving variables around and keeping signs and just getting accustomed to the algebra of moving numbers and variables together. That's the main practice behind it. Because even to this day, there are many students, especially when you get to a lot of the sciences, a lot of students have a lot of problems with solving for a specific dependent variable. You know, if you've got 3 variables in a string and you gotta solve for one of them, that process of back in the, you know, standard form stuff, that helps that background knowledge. That's the main reason why you see it. You guys just flew through it a little bit quicker than others, that's all. So, questions on that? One thing I did forget to mention when I was talking about the standard form rules, the A value, and I should have meant, I completely forgot. A has to be positive. A has to be positive in order for that to work. So sometimes it might, and remember the A value is always the coefficient of X. Sometimes it might be moved around. It's very, very rare that you see that in this book. But just one quick thing, and I completely forgot to mention that A has to be positive in order for it to work. And that's about all we have on that. Questions so far? All right. Horizontal and vertical lines. This is another one of those quick things that sometimes people tend to forget. Yes, sir?
What if A, B, and C were negative? Could that work?
If A, B, and C were negative, as long as you move it around so that A is positive, it's fine. A will always have to be positive. So if you're starting a problem with A, B, and C all negative, just flip-flop the B and the A and the B to the other side, and you'll be fine. Because B can be negative all day
Or
long.
could you just multiply them all by negative 4?
Yeah, that would work as well. Because when you multiply by negative 1, you're just flip-flopping off the sides. Yeah, that's fine. That's perfectly fine. Horizontal lines. Remember, horizontal lines have a slope of what? 0. Okay. And every single horizontal line has the exact same equation to start with. What letter does every single horizontal line equation start with?
0.
Y. Every horizontal line is always y equals a number. Because if you think about it, every single horizontal line will go through the y-axis, wherever that number is. Same thing goes with the vertical line. Every single vertical line will always be x equals some number. And one of those two is not a function. Which one? Vertical, very good. Obviously, it doesn't pass the vertical line test. It would be the test, yes. Unless you were lying down there. He just puts his head down and scratches. I don't even know what he's talking about. But yeah, I make things up a lot, you know, like my slope sort.
What happened? Oh.
12th hour, like 12th hour class, they were so mad at me. They were so believing the whole thing. They were like, what do you mean that's not? Why? They were ready to throw books at me. I mean, it was great that I've never seen anybody get so upset about being fibbed to. I love my job. Let's see, let's do that one. All right. Once again, not worrying about graph paper for you right now. If we do some graphing later today, I'm not sure. I'm trying to decide if I even want to give you graph paper to do some stuff. I think the idea of being able to spatially do it on your own is kind of a good idea. But just for example here, if I have a slope of -2 and a b value of 0, where does that start? Correct. So where would this start?
Here.
Okay. I just wanted to make sure you remember that. You'd be surprised sometimes people go 2. Now, if I'm starting at 0, my slope is -2. What's my first step? Remember, your first step is always going to be up or down, then go to the right. Okay? Things like that. Your first step, if you remember, your first step is either up or down. Positive being good, going down is you're going usually bad because you're going to burn or whatever. Once again, I'm making stuff up. And I'm trying to think if there's anything else crazy. That's slope intercept, that's boring. Okay, once again, let's try a quick graph. This is one of those examples that it is very simple because y is already by itself. You could just move the 2x over to the other side and plot it via slope-intercept form if you ever so are inclined. But now that you see the cover and solve method, you might be a little bit happier with that. What's your y-intercept? What's your x-intercept? There you go. Now, the only thing that you guys might accidentally do as you go through these things, besides missing the lines, the only thing you guys might accidentally do is just flip-flop your x and y value. Just slow your brain down real quick. Remember what you're solving for. Okay. Where do you think you put your x-intercept? Where do you put your y-intercept? Okay. Yeah, that's enough. Quick graphs are rather simple. What we got? 15 minutes? All right. Let's do this. Can you steal your book real fast, please? Oops, sorry. Which we're chapter 3. Chapter 3 is fun. Here's what I want you to do. What is that? 9 problems? You think you can handle that? Yeah. Let's do this. Do you want graph paper for this? No. No, you want to just fudge it on a piece of paper?